topics, image processing. Okay, I mean, I never thought how mathematics would be really applicable, until I was there, one of the microscopy institutes when I had a chance to really look at how it can make a difference. Okay, so I mean, this has lots of ramifications. This particular topic on how images are getting processed and things like that, from MRI scans to anything that you can imagine. It's one of the classic applications of the real mathematics, or what's so called as pure mathematics, into streams of engineering. Okay, so how many of you here have an idea of Fourier transforms? Have you heard of that? Right, right. So what does Fourier transform do? I mean, as an integral transforms in a more in a more in a bigger picture, right? So if you recall the linear algebra, remember we had what does linear algebra do? You have some bunch of vectors, right? And those vectors are translated to having the coordinates, right? What is meant by a vector? It has coordinates and it can be expressed in terms of the basis vectors, right? Similarly, you can think of functions. Right? Functions are also vectors, and you can think of adding two functions and subtracting two functions and things like that, right? It forms a vector space. So you can think of basis for a vectors for a set of functions. Okay, and that's what Fourier transforms are all about. It is trying to express functions in terms of sines and cosines, which forms the basis on the functional space. Okay, so that's what exactly. I mean, Fourier transforms are nothing but linear algebra at the end of the day. Okay, so it's one of the classic applications where we will see how really it makes a difference in image processing. Okay, so let's get it started. Image processing, it's again, like all the topics that we have discussed so far. It's a semester long course in computer science department, so we will only have a chance to go through some of the very important ideas. It has, I mean, it's like I said, there are so much of topics in this image processing that it will be difficult to cover. So it's just a snapshot of what the subject is. Okay, first we will go over digital image fundamentals, like where we can see relationship between pixels and how connectivity is a big problem, like the basic problem in image processing, how it produces paradox. And we will see some signal processing background. You already saw some Fourier transforms, and we will also see a little bit cousins of Fourier transforms. Okay, and we will see some Fourier transform applications, how Fourier transform essentially means, what it means when it applied to images. Can we infer something out of Fourier transforms? And we can really see what happens when we apply to real images. Okay, so it's all pictures. This class is more or less about pictures. And there is one important topic in image sampling. Like if you take any textbooks, fundamentals of signal processing, this is the basic uh, uh, theorem, which is known as a Whittaker-Shannon sampling theorem. How should we sample to reconstruct the signal, right? All things come in discrete packets, right? Everything that we are sampling, right? But we want to have a continuous information. So this theorem established something very fundamental. Okay, and we will see some image enhancement techniques, geometrical image transformations and interpolation methods. And we will also see image restorations, various noise models and various filters. There are really big topics in here, like image segmentation, texture and stuff like that, which I'm not going into. But it's all when we talk about image processing, those are critical aspects of image processing. For instance, when you have an MRI scan, you may want to segment certain areas of it, right? How these scans are all done, right? So, but we will not go over any of those. Image fundamentals. Image is nothing but a 2D light intensity function, right? This function is denoted by f of xy, where it denotes an amplitude of the spatial coordinates, right? So at every coordinate x comma y, you have an intensity value, the brightness value, or the signal, right? So it's characterized by two components. One is that the amount of source incident light, that falls on the scene, which is denoted by I of xy, and the amount of light that is reflected by the objects. It's called reflectance, so which is denoted by R of xy. But in general, the total absorption, right, it is denoted by R of xy equal to 0 is never achieved, because that's a total absorption, and R of xy is equal to 1 is never achieved, right? So this functions combines, and this two lies between 0 and infinity. So that's the very basics of digital image fundamentals, right? So for instance, for a computer to process an image, what are the two things that's required? One is that it needs coordinates, where the positions of these pixels are there, right? And you also need a quantization, which refers to amplitude or brightness at that particular coordinate, right? So the images are thus sampled only at discrete number of locations with a discrete number of brightness levels. The brightness levels may range from 0 to 32. Usually it's in the powers of 2, right? So these are called grayscales, right? So that's the idea. So for instance here, right, this is a height profile of Switzerland, and if you look at the aerial image, we can sample it, right, and you will get these sample profile of this Switzerland just like this. Or similarly, we can have quantize the intensity along any particular direction, right? If I profile the intensity along this, we will have this kind of a profile, right? And this is the quantized version of it, right? This is a continuous version of it, but if you are measuring at discrete locations, just like the sampling here, we will get this is the digitized version of it, right? So that's the basics of images. So in general, the digitization process, right, it requires you to make decision about two things: the size of the image, n by m matrix, and the number of grayscales allowed for each pixel. So this is f of xy. It is denoted by this matrix. This is an image. At the end of the day, this is the image that says that. So for instance, here 0, 0 has some intensity value. This 1, 0 pixel has some intensity value. So that's what it is about. It's just a matrix with some intensity values, right? In general, these quantities are the powers of 2, both for the purpose of storage and other things, which the computer is binary, so it's in the powers of 2, and also the grayscales, right? Both the matrices and the grayscales are in the power of 2. And we can ask main questions. Resolution, degree of discernible detail of an image depends on the number of samples and the gray levels. It depends on these two factors. There are three factors in here: xy coordinates and the intensity levels, right? So the bigger these parameters are, the closer the digitized array approximates to the original image, right? If you are able to sample as much as possible, right, and there are some limits to it. There's something called oversampling. We will not go into that. But the bigger these parameters are, we can hopefully try to recover the original image, right? But then the storage and processing time increases rapidly, right? These are very key components. If you have, you know how JPEG and other compression techniques work. So it's just some storage, right? It's tight, and then once you have it, open an image, it automatically computes that, right? Immediately it computes that. So it depends on the size of the image and the intensity, and the relationship between the pixels, right? The quantization does not imply a spatial structure. It must be defined. The spatial structure of an image should be defined, and we have to consider topology and other metrics on it as well. Okay, and the neighborhood is defined via metrics and vice. Right? I mean, the neighborhood, what is the neighborhood of a pixel? Those things have to be defined. Okay. So in general, in 2 dimensions, we can hope to have 4 or 8 or mixed down neighborhoods. Okay. So we'll see them now. But before that, we will define the following. A digital image is denoted by f of xy, like I said before, and pixels as p and q, and subset of the pixels as s. Okay. So 4 neighbors are simple. So for a pixel p, it just corresponds to these 4 neighbors, right? Those is a set of all the 4 neighborhood of P. Similarly, we can have diagonal neighbors, right? The diagonal neighbors are nothing but these 4 which are in the diagonals, right? And you can define an 8 neighborhood which composed of all the neighbors around that P, right? That's how you define the connectivity. So connectivity between the pixels is important in image processing because you have to establish so many things based on it. Like for instance, the boundaries, right? For instance, you have to connect the foreground and the background. You have to detect an edge, or we have to segment something. So we need to define what it means to have a connection between the pixels, right? So we can define, let's say, the two pixels P and Q are connected if they are in the 4 neighborhood. Let's say that 2 pixels are connected not in 8 but let's say in 4, okay, and the gray values satisfy certain criteria of similarity. Let's say that the gray values are same, okay. Will this distinguish foreground from the background? Let's say that you are defining one pixel is connected to the other if they are in 4 neighborhood, if they are in the 4 neighborhood, okay. Will this be enough to distinguish the background and the foreground? Right? That's the question. Actually, it's not, because let's say that this, right? For any of the pixel here, if it is in the 4, it may possibly distinguish, but these two, right? So for this is all connected, right? And so it's not able to distinguish these two. They are adjacent actually, right? You will not be able to properly separate the foreground from the background if you define the connectivity as 4 neighborhood. You get that? And similarly for 8 connectivity, right? So let's say that you have this, right? Let's say that the foreground and the background, if you say that this is a binary image, this is a 4 connectivity, and the 8 connectivity is this, right? All of them. But if you look at the background, right? The background are actually connected, right here, because they are 8 connected, right? So it's not able to still distinguish the background from the foreground, right? So the solution is to actually say that foreground is 8 neighborhood and the background is 4 neighborhood. And that way you can have a separation for the foreground and the background. Okay, this is based on Jordan's curve theorem. There is a famous mathematical theorem called Jordan's curve theorem, and this is based on that. Now, but this doesn't work for other grayscales. I mean, this is work for the binary images. Okay, but in general, it's very tough. This problem is exceedingly tough to separate what is a foreground and what is a background. I mean, these are all has to do with topological structures and other mathematical intricacies. Okay. If you look at the fundamental steps in image processing, you have an image, and then we pre-process the enhancement. This is one of the basic steps, and then we do a feature extraction, and some of these features we can group, and we can analyze the complex scene and then the output. These are the fundamental. Usually, this fundamental steps in image processing. Okay, but it differs. I mean, like for instance, if you want to do a noise removal, so that after pre-processing there may be a noise removal filter that we may have to apply. So these are all, but then in general, right, this is a typical example of how an image could be processed in a microscopy environment, right, or any other capturing environment. But in general, there are so many. It depends on the problem that you want to address. So I should say that it's not a fundamental steps in image processing. It's a typo. Probably it's an error. I should say that typical steps in image processing in a typical microscopy image or something like that. Okay. All right. So that gives you a sufficient introduction to a digital image, right? Now let's go into signal processing background. This is one of the classic images. You have the picture of a moon here, and this is a Fourier spectrum of it. And if we take these, remove these frequencies here, you see a much better picture here, right? I mean, some of these are well defined than here. Some you can see much more clear image. Like for instance, this is corrupted by some higher frequency noises, right? So this is an example, and how this is done. The first idea is this: any periodic function, right? Tell me a periodic function. Sin x, cosine x, all right, or some of these can be represented as a sum of sines and cosines of different frequencies multiplied by coefficient. This is a basic Fourier series. Okay, Non-periodic functions can also be represented as an integral of sines and cosines multiplied by the weighting function. This is Fourier transform. Okay, so Fourier series and Fourier transforms are more or less similar. So this is the Fourier transforms. You have a function f, and you transform this function f by taking the integral. This looks a little scary, but from minus infinity to infinity. But think about it. What is the e power minus this function do actually? Forget the j here. J is an imaginary number. But what does it do? The function actually reduces really rapidly, right? So when you multiply whatever function, bigger function it is, when you are multiplying by an exponentially decaying function, you are going to have a bounded sum, right? That's essentially the idea. Although it is from minus infinity to infinity, it doesn't matter. It's going to converge. I mean, for reasonably good functions, right? Within quotes and quotes. Let's not go into the details of those functional, what functions converge on Fourier series and stuff like that. But in general, right? So, and also this invert, one of the nice properties of this transform is that we can invert and get back the original function by taking the Fourier transform and then multiplying by the conjugate of this, right? So what essentially we are doing here is we are actually splitting the function into two components, okay? So this is the basic idea again in linear algebra. When you have it, you can break it into two components, right? So these are all what is known as a dual spaces, okay? So we can do that in when you have a functional space. So the Fourier transform pair, they exist, okay? For generally from functions, you have a function and its Fourier transform, they always exist, and it's almost satisfied in practice. Almost all functions have it, right? And actually, if you look at it, you are multiplying by what is e power ix cosine x plus I sin x, right? There is an imaginary component in there. So in general, the Fourier transform will have imaginary components, right? And this is a real part of u, and this is an imaginary part of u, right? And in general, we denote this f of u. We can write it as mod f of u times e power. So this is what is the magnitude, which is known as a Fourier spectrum, and this is the phase. Okay, so this is a phase angle, and these have meanings. Okay, so in general, the phase, the power spectrum, and the square of this, the power spectrum, is called the spectral density. Okay, and the variable u that appears in the Fourier transform is called the frequency variable. Okay, and so we can have this as a basic function. So this is a fundamental idea of what a Fourier transform is, right? So let's see an example of a function and its Fourier transform. So a function is defined by a if it lies between 0 and x, and if it is 0 otherwise, and the Fourier transform is kind of this. This is absolute value of the Fourier transform. You see that this is a Fourier spectrum. Why is this? It's simple actually. You take the function and you integrate it, right, from negative infinity to infinity, e power minus 2 pi nu ux, right? And so this is defined only between 0 and x. So the integral reduces this to this, and we can integrate some basic mathematics. We can see that this is a by pi mu of this function here. Okay. So as such, Fourier transform is a continuous transformation. You have a function, you have a continuous function, but in general we need things that we see, right? You get in a computer are discretized, right? Bits, it's made up of bits, right? Zeros and ones. So it's a discrete. So discrete Fourier transform is a discrete analog of the Fourier transforms, and in image is a two-dimensional quantity. We need the discrete Fourier transforms in 2 dimensions, right? So that is defined by this. It's similar. It's the same idea here. Instead of one single integral, we have a double integral, which translates to double summation. You have a function, and it's multiplied by this. I mean, it's as simple as that. And the inverse of DFT is given by this. It's exactly same as what we saw in the Fourier transform. It's just a discretized version in 2 dimensions. Okay, so that's a simple. So what's the use of? So if you look at the Fourier transform here, there are two things here. One is that there are two variables, right? You have x and y, right? So if you want to compute Fourier transforms in 2 dimensions, how many operations do you want to perform? Remember the algorithms class? You have, let's say that you have n particles, okay? you want to compute the interaction between any two particles. So yeah, so what's that, nm, right? So it's, if m is equal to n, it's n squared, right? So it's in the order of n squared, right? So it's very difficult to it's very difficult to compute in real time because this time is going to be huge, right? And for that there is something called as a fast Fourier transform. Have you heard of this term, FFTs, fast Fourier transform? So what they do is they compute the discrete Fourier transform in a fast and efficient manner. Actually, what they do is they make this matrix, you can represent this matrix as a diagonal matrix, and so the computations becomes easier in a more in a more general terms, right? So you can do the computation in n log n time, which is almost, they call it as pseudo linear. It's almost linear time. Okay, so that's why we are able to do this, and this is very important for image compression and things like that. You want to, and all these movies and things are made possible just because of this fast Fourier transform, because it's, you can compute it in a very efficient time. And this decomposition is this famous FFT algorithms. So for instance, an FFT of size 8192, let's say that it takes a particular machine in 1 second, okay? So using the DFT, you can see how much it's going to take. I mean, this is just a basic signal for n squared, right? This is the amount of minutes and hours it's going to take if you are not using the fast Fourier transform. So it has reduced our life so. I mean, I think this is one of the best algorithms of the 20th century or something like that. I mean, there was a there was an article that listed one of the best algorithms, and I mean, everything is made possible because of fast Fourier transforms. Okay, so all it does is it takes the discrete Fourier transforms and it efficiently computes it. So that's the idea behind that. So the dynamic, usually the difference between the smallest and the largest components of Fourier spectra is usually higher. So only the brightest paths are in general shown, and that's why usually people take the logarithm version of the Fourier transform. It's c times log 1 plus f of u comma v. So we can see that as an example. So here is an image of Saturn. And if you just take this Fourier transform, right, you are just going to see that one bright dot in here, right? Because only the largest spectra are shown, right? I mean, that's when you take it, the Fourier spectra, and that's why if you take the log transformation, you see a much more better Fourier spectra. I mean, as such, you may say that, okay, this doesn't mean anything, but it means a lot actually. Everything is done, it's best done in the Fourier space. Why? Why? Because of, have you heard of convolution, right? So what does Fourier transform get you? If you convolve two signals in the domain space, and if you take it to the frequency space, what happens? Right, it becomes a multiplication. So that's one of the biggest advantage of going to the frequency space. But yeah, we will see that in a little more detail. So the Fourier transform applications, right? First, we will investigate the basis functions of the Fourier transform. So if you look at the Fourier transform, it's cos x plus I sin x, right? I mean, the real is more or less a cosine, right? And this is known as this has a special name called as a cosine transformation. Okay. So in general, if you look at only the real space of it, it's a cosine like images, and that's what we are seeing here. So it has a pure cosine component, and let's find some of the primitive applications of this. Okay, so let's say that this is an image that consists of cosine of 8 cycles here and a pure vertical cosine of 32 cycles here. Okay, so this is just a cosine cycle, and we see that the Fourier transform is just a single component, right? I mean, it's just two bright spots around the center spot, right? The center is the origin of this coordinate system, and this is what you will see when you take the Fourier transform it. And this is the u-axis, and this is a v-axis, and we are only dealing with the real part of the Fourier transformation. Okay, so in both cases there is a dot in the center, right? That image that represents. But what we also see that the low frequency information have a bright blob, okay, that we will see it a little bit later. But in general, it denotes an average value. The center dot is usually the average value, okay? And the high frequencies in the vertical direction, right? If you have a high frequency in the vertical direction, that will correspond to dot in the horizontal direction and vice versa, okay? So this is just a purely the basis cosine transform. And here, in this case, let's say that we combine here with two of the cosines. One is on the horizontal and the other is on the vertical. And we see that these vertical, right? I mean, you have a symmetric Fourier transform here. You have two dots here, right? And similarly, you have this here. Now, the thing is, there's lots of symmetry actually, okay, in the Fourier transform. If you have both vertical and horizontal components, the Fourier transform will be symmetrical about the origin, okay? And that's basically because if you look at the cosine, right, in the first and the third quadrant, cosines are positive. And so you will have these Fourier transforms as it represents the in fact the it will be symmetric about the origin in the first and third quadrants if we take the cosine transform, okay? Let's look at this. The same image here, and slightly we are trying to change the rotating it, right? And you immediately see obviously this has the three dots that we previously saw, and now here you have some crazy things that's coming in between, and there is also a line, the diagonal line that you can see, right? So this is kind of why do we have that? That is because what happens is that when you have these edges, right? These edges, the Fourier transform it takes into consideration a periodic representation of the original image, okay? And that is why you have those effects in there. But if you are trying to kind of blur it, right? You can see it is becoming more and more horizontal. I mean, you can see that it's much more getting, you have a white blob here and it's more diagonal, right? You don't see these effects at all, right? So that's because of the edge effect. So in general, if you have edges, right, it's going to produce some strong contrast in your Fourier transform images, okay? So if you have, we will see an example of that in more detail, but in general, if you have strong edges, right, the edges of the images will tend to produce a sharper contrast with high frequencies in there, just like you see it here, okay? So let's see that. So actually, let's go into some of the real images here. So for instance, it's good. So here you see a Goofy and a blurred version of Goofy, and we see the Fourier transform of these two images in here. And first of all, we notice that there is a big sharp line here, right? And we see that the noise here on the horizontal direction is lessened out, right? So those are the crucial observations here, and that's due to the fact that this image, right, this was degraded in the horizontal direction, and so you see that there are frequencies lost in this direction, right? And that's one of the important points. Like the Fourier transform tend to reflect how the image, in which direction the image is degraded. Okay, so you can identify by noting its Fourier spectrum, right? And also it has a slightly large background noise. So if you look at these here, right, there is a slightly large background noise compared to here, right? I mean, this is all large background noise. And I think that's probably because they have introduced more random noise in this image, and that's the reflection. I mean, it reflects those information. And so that's how the general images will look like in general when you know these degraded images, and we can kind of get a sense of looking into this Fourier transform. I mean, as such, it will not make sense, but if you play with the images, if you take a cosine image and then see how you can try to interpret what's happening by looking at the Fourier transform. So for instance here, so look at this, has a strong periodic components in here. This is an image of a brick. and you have a strong periodic components here, and that's that's because when you have, right, I mean when you have these kinds of contrast, then the Fourier transform changes automatically. So when you have these lines, these edges, the Fourier transform is going to immediately have those components in there. So it takes a lot of high frequency power to follow such an edge, right? I mean, because it's such a line. Actually, if you look at the magnitude spectrum, the spectrum in the magnitude, you will see that. I mean, for instance, in this, right, in this cube, you will see that there is all these kinds of lines that's caused by the sharp edges the image is having, right? So this is the message. When you have sharp edges, it's going to reflect a high contrast in Fourier transforms and possibly include high frequency information in there. Okay. All right. So let's look at some of the shapes in here. So these ones, right? You see that there is this horizontal component. When you have it, there's tends to be a higher frequency here, and also when you have the diagonal, that's reflected by this line, right? And the ones that you have a circular shape is going to have some kind of a circle in the Fourier transform as well, right? And we can see some of these, like for instance K has these two, right? And so you will have these two information. So I mean you can look at some of these Fourier transforms, and this one, right, for instance, let's look at this one. There's lots of small beads in here, and that palette is reflected by this Fourier transform. It's not for all the images. Even if you take a single image, one bead, that's going to produce this Fourier transform, because we are only looking at the magnitude spectrum. So Fourier transformation also has the phase spectrum, that also has the angle information in there. So without that, we will not be able to identify what is there, what is where, but you will be able to see what is the general frequency in which the image appears, right? So that's and like and this is the Fourier transform of the coffee bean here, and you see there is a small halo in here. What do you think that halo is? Take a guess. I mean, yeah. So that's a contrast. I think it's in between the yeah, the bean. So yes, so that's some of the things, and these are the first truly general images, right? I mean, there is a very little structure in the Fourier transform if you look at the general image. So when we look at this, is the famous Lena in digital signal processing, image processing, and we see that there is this line. I think that probably reflects the sharp edge that's between these two, the hat, which is between the hair and the mane, right? And also the mandrel also appears to have some sharp frequency here, and that possibly is basically because of these hairs that has a contrast from this line here, right? So how about this image? This is the CFAN. CFAN is a weed, and this has lots of little holes in there, and the frequency or about half. If you analyze the image, it's about half to the maximum, right? And there is also a strong horizontal components of this. If you look at, so this, you can kind of see that there is also this has the contrast of the white and black in here, which is kind of reflected in this Fourier transform. And how about this? You have two vertical trees in here, right? This two vertical trees corresponds to the horizontal component, a strong horizontal component in here. So by closely looking at some of these, we will be able to infer from the Fourier transform of how the image could possibly be constructed, right? So this is a totally random set of pixels, right? And this is the Fourier transform of it. And if you look at closely, actually it's not visible here. There's a white dot in the center. Are you able to see a white dot here in center? Why is it there? Why do you see the white dot there? And why does the noise, Fourier transform of the noise, look gray? So what does the center represent in the Fourier transform? It's an average value. Okay, so that's the magnitude, average magnitude, right? And there is a mathematics of why that is true. So if you have this Fourier transform, right, you can see, you can generally think of it as a collection of a random noise is just a white noise, right? It's just a uh, things going up and down, and it averages to zero, right? So that is reflected by the Fourier transform with a dot, white dot that's in the center, okay? And the variance is what the average color should be. And the variance, the formula for the variance, actually you can derive this formula. I don't want to go into the mathematics of it, but you can see the expected value of the Fourier transform is given by 0, and that is why you see a bright dot in there. Okay, it is an average value, and that's why everything is going there. Okay, so you see that the white, and also the variance is in general, that's gray, right? I mean, because of the, you can calculate the variance of it and it will come out to some constant, and that constant is the grayscale that you see in here. Okay, so that's the idea behind the white transform. Okay, now we are coming to a very important topic, which is image sampling, right? So in general, what you have is you have a signal that comes, continuous signal like sunlight or any light, right? And we have a sensor, let's say a digital camera or a microscope or anything like that, and that's going to take these photons, right, which are discrete packets, right? It's going to be in discrete places, right? So at the end of the day, you are measuring the brightness information at only at selective places. You are not collecting the information at all places, right? So we have to get back the original image only from the sampled points that you get, right? How effective is this process? So so that's the idea behind this. So if you have this Dirac impulses, right? I mean, you are trying to sample at the set of points, and that's what you're doing. You have a function, which is a continuous function, like brightness or sunlight, right? And let's say that function vanishes outside a certain, the Fourier transform of the function vanishes outside this interval, okay? So when you have it, right, I mean, you can obtain a sampled version of this function, right? You multiply, and you're sampling this function here, 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 whatever, I mean, at several places, and that function is called a sampling function, okay? Let's say that it's s of x, and let's say that it has a constant distance from each other, okay? So you're sampling this function at various places, here, 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 and things like that, okay? And let's say, and the Fourier transform of the sampled function is again a sampling function, but it will have minus 1 over delta x. That's the difference that it will be separated, okay? So you can work out that the sampling function will be spaced 1 by delta x, okay, if you have a delta x separation. Now the convolution on the original signal domain is equivalent to the product in the frequency domain, right, and vice versa. And if you're taking the product of these functions, which is sampling, you have to convolve these functions in here, right? So when you convolve these functions, what happens? Look at that. When it is very close by, right? When delta x is very close by, it's going to be really separated. But if you take a larger space, it's going to correspond to a smaller space, right? And you will have aliasing that takes place. Okay, so it's going to mix up, and you will not be able to recover that signal at all. Okay, but if you select the sampling interval to be really, really small, that would correspond to a larger spacing in the Fourier domain, and you will be able to sample this properly. Okay, and with that we can take a window function. So once you have sampled in the Fourier domain, we can take this interval and recover back the original function perfectly well. Okay, so this is the famous Whittaker-Shannon sampling theorem. Okay, how you should be sampling your data so you can recover back the signal. Let's say that you are sending an image to your friend, okay, and your friend will be getting only a how much bits that you should send so that she can get, or he can get the original image back. It's a classic application of Shannon. So you have to send so that the spacing, right, it's really, really small, so that they can whoever gets it can recover it. But you don't have to send extremely small, right? I mean, there is an optimum level that you can send. Still, the person on the other end can receive your signal intact. And this famous theorem is the Shannon sampling theorem. And this frequency in which you have to sample is called the Nyquist frequency. Okay, so whenever when you're taking an imaging in microscope, there is also an adjustment that say Nyquist frequency, right? Have you heard of Nyquist frequency? So this frequency is called as a Nyquist frequency for sampling, so that you can recover back the image. Okay, and mathematically, since Fourier transform of a sinc function is same as a rectangular function, we can do it as a convolution, and we can write this. So you can recover the function by using a sinc function. Okay, so for instance, like here is an example of an original pattern, and you apply a sinc function of size 5. You get the sampled points, and you see that the recovered image is really bad. This is an example, classic example of aliasing. Okay, but an example of a good reconstruction is this: if you have a sinc function of this, and you can recover back the image perfectly fine. Okay, so it depends on your image as well as it depends on the way that you sample your function, right? All right, let's go into another topic, which is image enhancement. Okay, so the principal objective here is to process image so the results are more suitable than the original images. Okay, so it's a we have to make how you want to transform some images if you want to find out certain features of it, right, and things like that. So this approaches usually falls under the category of geometrical image correction. Okay, so what it means is that you have a function, you have an image, and you want to transform. Nowadays, you see that in Photoshop and everything, right? You can transform the image, and all these are all made possible because of the underlying mathematical transformations, matrices actually at the end of the day, right? So the transformation H is either known in advance or can be determined from several known pixel correspondences in the image and the transformed image. Okay, so depending on the geometrical distribution, so you can choose. So for instance, this is an image, and you are trying to transform. So it can be determined either you can know the transformation H, or you can try to compute H inverse to find the transformation. Okay, so what two things you are needed for transformation? One is that we need to map the coordinates from the input image to the output image, right? And the output coordinates generally fall into exactly pixel coordinates. There are some difficulties in there. And how we are going to do it, right? I mean, also the brightness, we have to determine the brightness levels of the new transformed image. So two things are required, okay? So this is known as an interpolation problem. We'll study that a little later. But first we will see how some of the mappings are done. This is a classic, it's an 18th, 17th century ideas on projective geometries are now actually finding real applications. Okay, it's called a projective linear group, and these projections have been studied for forever. A group can be split into various subgroups with special properties of increasing complexity. Okay, the first is called isometry. Isometries are distance preserving. Okay, they preserve the distance. They don't change the distance. And you have similarity transformations, which can change the distance, but the scale also should be okay. And there are something called as affine transformations. Those are linear transformations, and there are projective transformations. Okay, the most general case of a geometric transformation is a free form, free curve. We will not cover that, but there is a good mathematics behind free forms. Okay, first we will look at isometries. Isometries are preserve the same distance. And so, for instance, if you rotate an image, right, that's an isometry, because if you take any two distance in the original image, it's going to be maintained in the rotated image. That doesn't change anything, right? So or you can translate the image, and these are all isometries. And in general, the isometries are given by this H isometry of x. The new coordinates of x is given by R matrix, the rotation matrix, the translation matrix, and this is a null vector and 1 of this x. So if you have, this is the transformed image. So let's say that they have 3 degrees of freedom, 1 for rotation and 2 for translation, right? You can translate it on the x direction or translate it on the y direction, right? So that's the correspondence. And the invariant of isometries are lengths, obviously, angles and area. They are just kept the same. So for instance, if theta equal to 45 and t is equal to minus 100 and 100, it will give this transformation. So the new pixel x, the old pixel x has to be multiplied to get the new pixel. So for instance here, right, this is just a simple isometric transformation, right? You're just rotating and taking negative 100, so the y-axis is moved negative 100, the x is moved negative 100, the y is moved negative 100, the image is rotated 45 degrees. Okay, so this is an isometry. There is another similarity there is a similarity transformation. It's called isotropy, which means that the scaling on the x and y remains the same. Either it's in the x direction or in the y direction, the scaling should remain the same. Okay, so it can change the distance, but the overall ratio should be maintained, and that has this form: h of the similarity x. You take this, you have a scale factor, you have the rotation t, and the same matrix here. So how many degrees of freedom does it have? The previous had 3 for rotation and translations. Here there is one more, yes, right? So it has 4 degrees of freedom, right? 1 for rotation, 2 for translation, and 1 for the scaling factor, right? And similarity can be computed from 2-point correspondences, just like that. And the invariants are angles and parallel lines. The length between the point is not an invariant. The ratio of the two lengths are, right? So these are the, if you have this 45 degrees and the scale factor s, and you can see the effect of this transformation, right? You can shrink it, right? Whenever you want to take the image, it automatically does this, right? I mean, in preview and places, so it keeps the scale factor, right? Otherwise, the image is, so it just multiplies and then it shrinks the image having the scale factor in here. And the third class of geometry or transformation that you call as affine transformation. So affine transformation in general takes, it can skew, rotate, or scale. It takes a matrix A instead of the rotation, and the rest of them are just the same, right? This is orientation preserving or reversing if the determinant of A is positive or negative. Okay, so it has 6 degrees of freedom: 4 for the non-singular matrix, 2 for the translations, and 1 for the well, yeah. So I mean, yeah, just 2 for it. There's no scaling here. And the invariants are parallel lines or mapped to parallel lines. The ratio of the lengths are the same, and the ratio of the area of the same. So for instance, let's take the A matrix as this and do an affine transformation on this, and you see that it's transformed in an affine way, right? I mean, it's just it's changed in a different direction, and it's just having the rest of the ratios, right? And also the fourth is known as a projective transformation. And what you have here is there is a matrix A and there is a vector V, right? And this is a projection matrix, and there is also a translation vector. So this is a parameter, okay? This is not a variable, but just a parameter. And so you have 4 and then 2 for the degree of freedom, and you have 8 degrees of freedom for this affine transformation, for projective transformation. And it can be computed with 4-point correspondences. Okay, so this is a projective transformation, an example of a projective transformation with the same matrix there, and you see that you can transform this picture like that, right? I mean, you can. It's just this is just an example of transforming the whole image. You can take a segment of the image and still transform and do that, right? I mean, you can transform the face, you can transform, like, features of a particular image, right? But the idea is just going to be the same. All right. Once we have transformed, one of the key things is so what does the transformation require? One is where the new data is going to land, right? The pixel is going to land, and the intensity. And that's where the interpolation comes in. There are 2 common approaches, right? One is called as a forward mapping, taking, okay, this is a pixel here, and I'm going to transform it to another pixel there, and what's the intensity that it has to have? I can compute it from the original image. And that's called a forward mapping. And backward mapping is reverse. You take the H inverse and compute what the original pixel is, and then you apply it there, right? So during the forward mapping, you have there are problems in here. For instance, they don't fall into exact same pixel location. One pixel location may fall into multiple 2 pixel locations can fall into the same. So there are some issues in here, right? I mean, this is not a 1-to-1 transformation. That's the biggest problem in here. These are multiple transformations, right? I mean, this is not many-to-one function. And they may not get some value at all. There will be gaps in it. But there are some problems. I mean, there are some ways to do that. But in general, the backward mapping can be computed in a much more efficient way, and this approach still suffers from the problem that if you have a pixel here, it may not fall into exact one location here, but it can be efficiently computed. So in backward mapping, right, you need to know the function h inverse, and the pixel location can be looked into the original image and try to infer what could be the possible pixel value that it's going to take in the new image, right? I mean, it's going to be, and it is generally computationally faster. There are problems in there, however, but there are three approaches to do it. One is the nearest neighbor method. The second is the bilinear interpolation, and there are cubic convolution methods. Okay, we are not going to. There are so many methods for interpolation. It's another huge area, but we are just going to look at these. So, what the nearest neighbor does it sets the intensity right into the closest pixel, takes the nearest neighbors of those pixel in the original image, and then keeps that as the intensity. Right? There are advantages and disadvantages. It's very fast. Right? You just need to look it up once. Right? And it does not introduce any new gray levels in the image, although interpolation shows heavy artifacts. I mean, think about it. These are all critical issues when it comes to, let's say, scanning an MRI image for a patient, and you may don't want to change the gray values. I mean, which could mean a disease or no disease, right? I mean, these are extremely important from a point of view of practical applications, right? So, for instance, nearest neighbor is you can assign this to here, right? And that's where probably machine learning might also be helpful, combining with image processing, right? I mean, if the patient has been diagnosed of some disease, irrespective of the image, then possibly we can use that information to learn back how images can be accurately, classified for a disease prognostic or not, right? I mean, those things, or diagnosis, right? So these things can be done. Bilinear interpolation takes the pixel values from the four closest pixel values, and it takes a weighting, averaging, and this is the formulae for weighting and computation of the new pixel. So what it does is it just takes these four values. I don't have a picture here. Okay, it just takes these four values and computes it, right? And similarly, we can have, oh here, yeah, I have it. So we have this, and the weighting function, it chooses appropriately. So if this is going to be farther, then this W1 is going to be more. So this is how the weighting functions are chosen for the, and there are cubic convolution methods. So instead of just taking single neighbor or four neighbors, the cubic convolution takes into 16 neighbors and then does the computation for finding the intensity value of the pixel, right? The cubic convolution is better at retaining the original gray value than nearest neighbor or bilinear interpolation, but the computationally it's very expensive. We have to do that. I mean, we have to think about the computation from an image net of 42 million images, right? I mean, it's prohibitively expensive, and even these small things can make a huge difference between computing in a day or computing in 10 years, right? So these are all. But here is an example. Here is a nearest neighbor interpolation, and this is the. I think this is the bilinear interpolation, and you already see that this is much more refined, better than the nearest neighbor, and I think the cubic convolution is similar. I looked up the difference together, but I think it's more or less the same. But there are some applications where the cubic convolution might be really make a difference than either using any of these methods. So from my research, or very rudimentary research, that I found that cubic convolution is a very good method compared to these two, although in this particular example it really doesn't matter. Okay, in contrast to image enhancement, let's go to another topic of image restoration, right? This is not just image enhancement, but image restoration, right? We have to take into consideration how an image, a distorted image, you get distorted image all the time, right? And how we can try to make it better, right? We have to reconstruct it. And usually the idea behind the images is you have a function, you have an image that's coming from here. It could be anything that comes, and there is a degradation function h, and you have a noise that gets added to it, and this is the image, the noisy image that we get, and we can apply some restoration techniques to get an approximate value of the function. So this is a general model, and we have to find restoration. And in general, this is the mathematical formulae. You have a function g of x comma y that is convolved with h of x comma y, plus you have the noise. And in the Fourier transform, the convolution translates to multiplication. So it's a pretty straightforward one. But there are various noise models that we need to consider. And the performance of imaging sensors, right? I mean, they have very, it's sensitive to temperature, it's sensitive to light levels. Uh, you get Poisson noise all the time, and there are so many other distortions that can happen just due to the mechanics of it and the environment of it, right? So images can also be corrupted during transmission due to the interference in channel, for example, due to lighting, right? Or a specific noise source, right? We have to think about some specific noise source. So there are various models for it. The Gaussian noise is simple. This Gaussian noise happens all the time in several things, right? You have the white noise. The application, it's so convenient, it's easy, it's known, all the Gaussian formulae. And there is something called the Rayleigh noise. Usually, when we think of an image, it comes with a distribution that's called as a point spread function. Okay, so when you there's a pinhole camera, you pass a light in there, right? What you get is a distribution, and that's called as a Rayleigh distribution. And one of the Rayleigh distribution comes when the wind velocity is analyzed into two orthogonal components, and you have the noise, and that can be made as a explicit formula, and it is used for approximating skewed histograms. This is the formula for using the Rayleigh noise, right? And you have Erlang noise, and especially in laser imaging, you have this commonly occurs, both Erlang noise with these mean and variance, as well as you have the exponential noise. Exponential noise is similar, closer to Poisson noise, and so some of the things could be used from there and here. And negative exponential noise occurs in laser-based images. And this is a particular case of an Erlang noise model with b equals 1. Okay, so there are various noise models, and there is a uniform noise. When the real value from a sensor is discretized, the differences usually forms a uniform noise. And also there is something called as a salt and pepper noise, right? I mean, usually when you have the signal strength, or when you do a thresholding and you have the saturated values, when you're digitizing, you will see that there are lots of salt and pepper sprayed on it, right? I mean, that's a salt and pepper noise. And apart from that, there is something, a very critical noise. It's called a periodic noise. And this typically arises from electrical and electromechanical interference. And this, you see that most of the times actually. And these can be approximated by Fourier spectrum. There are a bunch of methods for taking out these periodic noise. And most of these can be detected by visual analysis, or we can, if we have the sensor, we can take the place where there is no noise and then use it as a background for subtraction, right? So that the periodic noise, for instance, here when we have this model, right, this is all corrupted by periodic noise. And if you look at the Fourier spectrum, you see the 4 dots in here correspond to this. I mean, so this is one of the nicest analysis of, using the Fourier domain, right? So when we have these kinds of noise, right, we can use this filters to remove this noise. For instance, here in this example, right, I can use only this area and take only that particular area, and that's going to remove the noise. And these are called filters. And we will see there are 3 main filters. One is a band reject filter, which means that it just allows everything outside the particular band, right? So for instance, in this case, it will just throw away this, there will be a small band where we can put and take away only those components, right? This is called as a band reject. And there is another filter called the Butterworth band reject. It's similar to band reject, but then it's a much more smoother approximation. And we have the Gaussian band reject filter that takes a Gaussian form. And these are again, it depends on the image, right? I mean, so for instance, here when we use all of these 3, it's almost the same, right? It immediately, this band reject filter gives you a very nice approximation of this image, right? So it takes away the noise that we are looking into. So, I mean, as I said, I mean, this is just an introduction for signal processing. It's a huge area, image processing. It's a huge area. It's a fascinating area. When we have the real MRI images and this along when you with this when used along with machine learning, it's like it can do really good things, right? I mean, so I mean, there is this. If you go into this page, the introduction to image processing, this guy has put lots of things. Very nice presentation. So, for instance, image segmentation. I didn't cover any aspect of image segmentation. It's a huge topic. Like, how do we select these parts in here, right? So let's look at a very brief things from image processing, from signal processing. I'm going to skip over all these. Let's look at the points and edges. Yeah. So you have an image here, and you see this. This is a very light, and then there is a point in here, and there is a dark things in here, and you have an edge in here. Again, it becomes dark and then light, right? So if you look at these values, you see that how the intensity is high, right, and then it goes down the intensity here, this area, and then for this isolated point, the intensity becomes high again, right? Just one point, and then goes down here, and you have the line. This is a flat segment that we have, and then this line, this small line, is represented by this peak, and then we have the step. Again, this is black, and then immediately there's a contrasting white in here. So you have this signal, and the image values are like this: 5, 5, 5, 4, 3, etc., etc. If you take the first derivative, right? First derivative, if you take the the discrete derivative, you can take this. You have this formulae, and you can take the second derivative, right? And you see that there are some neat things about the first order derivative produce thick edges. If you look at that, right? The magnitude of the second derivative is much stronger, and actually the fine line has a larger magnitude for the second derivative than the first, right? Minus 12, right? And that can identify the isolated point here, right? And also we have the second derivative as a small step for the negative ramp, right? And we have the double edge effect in here. We have the double edge. So we can look at these first order derivative. They produce thick edges than the second order derivatives, and they have a strong response to fine detail, right, such as points, lines, and noise. And the second order derivatives produce double edges, right? They produce double edges, and the sign of the second order derivative can be used to determine the polarity of the edge, whether the edge is going from negative to positive or positive to negative, right? So that could be a critical information. Like, advantage of knowing polarity is critical in some of these scans, right? Now the point is the point deduction. Like I said, the second derivative is higher, so we can compute using the point, using what is known as a Laplacian, right? You can try to find, and there are classic ways of finding the points and edges, and the three methods. I will leave all these for you to go and study. But then there is a sensitivity to noise can be analyzed, and there are three main methods of edge detection. One is the basic edge detection, and the second is let me skip all this: Roberts, Pivot, and Sobel. So these are the three classic edge detection methods of how you can determine the edge in the image. Okay, I mean, ultimately it comes to the analysis of the first and second order derivatives in your image. Okay, so I think it's a it's a fascinating area. Again, as I said, I mean, this is something that you can really see actually, right? When you see something that's working or not, it can be done by visual inspection, unlike working in genomics where we don't have any clue, right? And something like that. So this is like, for instance, there are ways of what is known as a blind deconvolution. You can take a point spread function and try to convolve, try to see if there you get a better image, and that could also be visually made, right? So that's one very important aspect of image processing. So if you want, I mean, people who are not yet thought about it, I would suggest you to strongly think about some of these, uh, areas for your future research. And I think it would be terrific, to have a good project combining image processing and machine learning. Okay. So with this, I think I will stop for today. Any questions? Feel free to ask me. I think the lecture is over. For me, I'll probably co-direct the machine learning class with David next semester. But meanwhile, if you're having any questions, if you're having interesting thoughts about projects in mind, feel free to write to me so we can work on it, right? All right. Thank you, guys.